Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will derive simple updating rules when we observe a random sample of size n from a normal distribution with mean mu and variance sigma squared, which is assumed to be known. The prior distribution that we're going to be considering is a normal with mean m and variance s squared. Let's begin. So perhaps you remember that we already talked about a very similar problem, right, under the same conditions, but in that case we only considered a single observation, a likelihood function with a single observation. So we want to extend those ideas for the case when instead of a single observation we have a sample of n observations. So first, let's talk about the likelihood of a sample if we are drawing observations from a normal distribution. Okay, so likelihood of a sample. So we have y1, we have y2, and we have yn. N observations. The unknown parameter here is mu. We are assuming that sigma squared is known, and we know that if we're considering a likelihood for a sample, right, and these guys are IID, independent and identically distributed, the likelihood is just the joint probability density for the sample of n observations, right? It's just the joint probability density for that vector, right? But since they are IID, independent and identically distributed, it's just the product of the individual likelihoods. So it's just the product of evaluating n times the PDF of a normal at each of these individual observations. Okay, so let me use the proportionality symbol here, and remember again that we're assuming that sigma squared is known, right? So that normalizing constant 1 over the square root of 2 pi times sigma is just a constant, so we're going to absorb that constant here with the proportionality symbol. So the only part that matters is the exponential, right? So here is e to the negative 1 divided by 2 times sigma squared times y1 minus mu squared. And then we're going to have times, we would have something really similar for the second observation, and so on. Up to the nth observation. Make sense? Last observation, n, second observation. Should have a 2 there. Okay? So then we can do a little bit of algebra. We know that we could combine those exponents, and then what we would have would be just, this is a common factor, we would have a sum, we would have a sum of n terms that look like this. Okay, there we are. That's it. Okay, so our likelihood is proportional to this. Okay, now let me remind you that we talked about the likelihood of a sample coming from a normal distribution in detail in another video, right? So I'm just going to summarize some of the ideas we discussed here for and we're just summarizing those here, even when we have already discussed them, to have a better context of this problem that we are tackling now, obtaining those updating rules. So what we did here, maybe you remember that what we did is we added y bar and subtracted a y bar. So basically what we did is we added a 0, right? And when you do that, you're not doing anything wrong, but that is going to help you to come up with an alternative expression for the likelihood, right? So what we did then is, and again let me remind you very quickly, what we did then is we expanded that exponent, right? We re-expressed this, that just happens to be the same as, well, we need the sum actually, so we need the whole thing. So that happens to be the same as the sum of the squares of the first term. Let me just square the first term, this one here, right? Then you're going to have 2 times the cross product, okay? And once you do that, this y bar minus mu is a common factor, right? So you can pull it out. So what you end up with is this 2 times y bar minus mu times summation of the summation of yi minus y bar, no squared. I will just change that here. Great, right? And then you have summation of I goes from 1 to n of y bar minus mu squared. So when you do that summation, you end up with n times that term. Make sense? N times that term squared, right? Leave that like that, right? So it looks nicer. Okay. Then what we said is this. Note that summation of yi's minus n times y bar, that is equal to 0. So in the end, the only terms that survive are the first one and the last one. Okay? So again, summation of yi's minus y bar is the same as summation of yi's minus n times y bar, and that happens to be 0. So we got rid of the second term, and only the first one and last one survive, right? So the point being is that now your likelihood for a sample is proportional to this. Instead of that, we will have that as our exponent. Okay? Now, note that, well, this guy here, that term here, doesn't involve mu, right, at all. So this one is going to be just, and sigma squared is known, so that's a constant, so we can absorb that using the proportionality symbol, right? So, but the other one, the n times y bar minus mu squared, that one involves mu, so that one we're going to keep. That's it, right? Now let me rearrange this. That n, we can pull it out, right? So let's pull it out. It will be useful. You'll see it in a sec. So we could have that n here instead. And furthermore, we could re-express that like this. Right? Okay. So what we did here is we started with the likelihood of a sample of size n, y1, y2, up to yn. And after we did a little bit of algebra, what we realize is that, guess what? You could think about y bar as your variable, and then y bar, we know, right, has a mean mu and variance sigma squared divided by n. But the thing is that the likelihood of a sample is proportional to the likelihood of the sample mean. Okay? Makes sense? But that means that instead, when you're considering a sample of size n, right, what you could do is just consider, right, instead the likelihood of y bar. You could think that as a single observation, and y bar has a normal distribution with mean mu and variance sigma squared divided by n. So what we did for a single observation translates immediately to the sample of size n case. Can you see it? Okay. So let's try and use this to come up with that updating rule for a sample. Okay. Now again, let me underline this. The thing is that after we played around with that likelihood for a sample, y1, y2 up to yn, we had n observations to consider here. We are trading that for a single quantity here for y bar, and y bar has a normal distribution with mean mu and variance sigma squared, and then what we know for one observation translates to being able to do something with a sample of size n. Make sense? Okay. So let's recall how that thing goes. Okay. first, remember that when we talked about those updating rules for a single observation, we introduced another concept, the concept of precision. Okay? So let me just remind you what we just did here, so we can use it. So, likelihood of y1 up to yn, right, in observations, is proportional to likelihood of y bar, right? We know that y bar has a normal distribution with mean mu and variance sigma squared divided by n, right? Okay, so in this case the precision, remember, precision of y bar, remember that the precision is just the reciprocal of your variance. So in this case the reciprocal of sigma squared divided by n is just n divided by sigma squared, right? That will be the precision of our y bar, which is the same as the precision of our sample. Make sense? Okay, now let's use those updating rules. Again, the thing is that we can think of y bar as a single observation from a normal with mean mu and variance sigma squared divided by n. So now let's try and remember how those updating rules work. Using updating rules. So we know that the posterior precision, and we are using S star squared to refer to the posterior variance. So since we're using S star squared for the posterior variance, then posterior precision is, you know, just the reciprocal 1 over S star squared, right? So what we said is, if you don't want to do the algebra and you want to obtain the posterior precision, the formula goes like this. Your posterior precision happens to be prior precision, remember, 1 over S squared, right? S represents our prior variance, right? Our prior standard deviation. S squared represents the prior variance. So anyway, posterior precision equals prior precision plus precision from your observation, this guy here. Okay, so again, posterior precision, just prior precision plus observation or sample precision, if you will, in this case, right? And once you have that, the formula for the posterior mean, remember that we use M star for the posterior mean, right? What we said when we talked about these updating rules for a single observation was this: hey, the posterior mean is going to be a weighted average between the prior mean and your observation. In this case, your observation is going to be y bar. But it's a weighted mean, right? So we have some factors here. And the factor that we're going to have here is what we said is those weights are going to be the proportions of the precisions, of the corresponding precisions. So in this case, right, what we have is your prior precision divided by posterior precision times prior mean. Okay, and then what you're going to have here, as you recall, would be, well, the observation precision divided by your posterior precision, right, times your observation. In this case, it's y bar. So again, posterior mean, just a weighted average between prior mean and your observation. So in this case, posterior mean would be a weighted average between prior mean and sample mean, and the weights that you have are the proportions of the prior precision in relation to the posterior precision. And then here you have the sample precision divided by the posterior precision, right? Okay, makes sense? If you will, you could call these guys W1, something like this. W1 would be that weight, and note that this guy here, the sum of these two weights is equal to 1. So another way of expressing this would be something like this: m star is equal to W1 times 1 minus W1. Times y bar, where W1 is given by that. Okay? So bottom line, if you want a shortcut by making that observation, oh, the sum of these guys, these fractions, is 1, right? Once you have this one, you get the other one for free. Okay? But again, what I wanted you to see here is that once you have the fact that the likelihood of a sample is basically equivalent to the likelihood of the sample mean, right? Your updating rules for a single observation are going to be useful to find the posterior distribution. Okay? And just same rules apply, right? What you have to remember, so you don't have to do the algebra all over again, is that posterior precision equals prior precision plus sample precision, right? And then the posterior mean is just a weighted average between prior mean and sample mean, and these weights just represent the proportions of the prior precision with respect to the posterior precision, and sample precision with respect to the posterior precision. Make sense? And another shortcut, if you want to save some time doing calculations, is once you have one of these weights, the other one is 1 minus, right? Because these guys are what mathematicians call a convex linear combination, meaning the sum of these weights equals 1. Okay, well, that's it. Thank you for watching. Please take care and keep working hard. See you next time. Bye.